Okay, so hi everybody. In Chapter 4 for AP Chemistry, the title of which is Aqueous Reactions and Solution Stoichiometry, there are parts of the chapter that we've covered and other parts that are totally and completely brand new to everybody. So to be on the safe side, I'm going to do a little bit of review on slides, I think it goes 1 through 31, which talks about, among other things, some types of chemical reactions, how to write net ionic equations, what makes something a strong or weak electrolyte, and talks about also the strong and weak acids and bases. So let's define a solution as a homogeneous mixture of two or more pure substances. In this case, looks like some copper sulfate in water. Solvent is the thing doing the dissolving, which by definition is the one that you have greater amounts of. The solute are the things that are getting dissolved. Sometimes it's a little unsure or unclear as to what you would call the solvent, especially if they're both in the same phase. So the air around you right now is a solution. I would call nitrogen the solvent because 80% of the air is nitrogen and the oxygen is less than 20%. Now we learned last year that when you throw something ionic into water, the positive and negative parts of water are attracted to the negative and positive parts of an ionic crystal. If you look carefully, you'll see in this graphic that we've got a picture of a chloride ion being surrounded by all the white hydrogens of water molecules turned inward. Hydrogens are positive, that's why they attract to and pull off the negative chlorides. And over here, notice that it is the negative oxygens that are surrounding the positive little purpley sodiums. So this is called dissociation when we take an ionic substance and we rip it apart in water. If you have an ionic substance or something that forms ions when you put it into water, then it can conduct electricity, and we call that an electrolyte. A non-electrolyte might dissolve like sugar molecules, but since the molecules themselves have no charge, they don't turn into ions, and as we learned in our demonstration last year, that electrolytes are substances which are good conductors of electricity. So soluble ionic compounds, and also you notice that there are some molecular substances like the strong acids, make strong electrolytes. Weak acids and weak bases do not make good electrolytes because they don't form very many ions in solution. So to have the flow of electricity, you have to have the ability for charges to flow. No charges, no flow, no electrical conduction. So molecular substances tend to be non-electrolytes, except things like acids and bases can actually undergo a kind of chemical reaction with water to form ions where theoretically none had been before. So when we did our demonstrations last year, we did a variety of predictions where we looked at will the light bulb light up or not light up. A strong electrolyte would be pictured over here on the far right hand side if you're able to see the relative intensity of the lighting. A non-electrolyte, no ions, no current. Strong electrolyte, lots of ions, lots of current flowing, bright light. And few ions would be things like acetic acid, for example, that has only 1% of itself turn into ions when put into solution. So we did this demonstration last year using the light bulb as a way to predict the strength of the electrolyte. Now here's the bad news. On the AP exam, you have to memorize the strong acids and the strong bases. You just got to know them. So some of them you already know, hydrochloric or sulfuric acid and nitric acid. We didn't work at all with hydrobromic, hydroiodic, chloric, or perchloric acid, but those 7 big strong acids you have to just know by sight. We'll be quizzing on these as well as quizzing on the strong bases. An easier way to remember the strong bases is anything hydroxide was typically a base. Anything made with group 1 metals, like the alkali metals of lithium, sodium, potassium, rubidium, they make strong bases. Also, the first 3 guys in group 2, calcium, strontium, and barium, those also make strong bases. The other metal hydroxides, the other group 2 metals, alkaline earth metals, do not make strong bases. Soluble ionic salts. This table should look familiar. I had you memorize both the top and the bottom, and again, you need to be able to know your solubility rules pretty much from memory as best you can. But you probably noticed that they happen like in groups of things like silver, mercury, and lead that were exceptions to being soluble. Or down here, you would have had some exceptions to being insoluble were guys like calcium, strontium, and barium. So you see that fairly often. Nothing I can really help you with on this. It's strictly rote memorization. Now we also learned last year that you can make a precipitation reaction form when you take two previously clear solutions and you get a solid forming, and in this interface between where the two clear solutions are is a solid, I'll guess that's probably lead iodide. What we called those reactions last year was double replacement reactions, but what they're truly called are metathesis or exchange reactions. And that comes from the Greek word that means transpose. And essentially you can see here that silver nitrate and potassium chloride shifted to make silver chloride and potassium nitrate. Maybe the easiest way is to just trade places with the first element in each of these ionic substances so metals can replace other metals. This was an easy one because it's already balanced, because all the charges on sodiums, or excuse me, on potassiums and chlorides and silvers and nitrates are all plus and minus 1. Now what you're going to find out in this chapter, and also again in chapter 20, is it's a little more complex than just two ions trading places in two compounds. And it actually is what we call a redox reaction, but there'll be more on that later. Do pay attention as you write these equations as to indicating whether things are solid, liquid, gas, or aqueous. And we have to be aware of what is changing in the course of one of these reactions. So now this should be a review. This was a molecular equation, or what I might have called the general equation. And it just shows things unsplit up. So anything that says aqueous are things that are actually dissolved in water. And these are shown in their molecular form. It's kind of confusing because all of these things are ionic. So they're just saying, write them as if the ions had not separated from each other. In reality, we learned last year that the water ripped apart the silvers from the nitrates and the potassiums from the chlorides. And what will happen is when some ions bump into each other, like potassiums bumping into nitrates in this ionic soup, nothing happens. But when silvers bump into chlorides, then you get a precipitate. So one of the first rules is that anything that is solid is always written as if they are attached to each other, because in the formation of a precipitate they are. But anything that was soluble in an aqueous solution, like silver nitrate or potassium chloride, you must represent them as being dissociated into their separate ions. Now that's an ionic equation, and I bet you can remember how we get to the next step. The net ionic equation consists of canceling out those ions, let's back up there, that are what we call spectator ions. And in this particular case, I can identify a spectator ion because it's not in the precipitates formula. So nitrates and potassiums are always going to be soluble. They'll never be making a precipitate of anything. And essentially you think of the arrow as an equal sign. Just like if you had X on the left of an equal sign and X on the right, they would cancel. The potassiums cancel each other out. The nitrates cancel each other out because those are spectator ions. They don't take part in the formation of the precipitate. And really, that's all scientists or chemists want. They want the net ionic equation that just shows the players, the things that actually react. Now, this is a reaction that goes to what we call completion. It formed a solid. Completion means it's like removed from the mix, so to speak. Another type of product that would go to completion would be a gas bubbling off. Or a third type might be if you have the formation of liquid water. So the things that don't change, that don't take part in the formation of the precipitate or liquid water or gas product, are called spectator ions. And when you write a net ionic equation Our process, as we learned in that ion lab last year where we wrote ionic equations, was write the regular general molecular equation, show everything that is a strong electrolyte as being split apart, cross off these spectator ions, and write what's left. And that is our net ionic equation. Now, I went through that kind of quickly because we spent quite a bit of time focusing on that, so that should definitely be reviewed. Now, we will be spending entire 2 or 3 chapters on acids and bases, but a quick definition of acids is the older one by the Swedish chemist Arrhenius, who said anything that can cause a greater concentration of hydrogen ions when dissolved in water is going to be defined as an acid. Well, Bronsted and Lowry came along sometime later and fine-tuned that definition and said, let's define an acid as anything that can donate a proton. Remember, a proton is essentially the same as a hydrogen ion. Hydrogen atoms have one proton, one electron. You lose the electron, all that's left is a proton. So you will hear the word proton and hydrogen ion used interchangeably because they are the same thing. Again, sad news is you will have to memorize the formulas of the 7 strong acids and their names. Now, the word strong doesn't have anything to do with concentration. The word strong has to do with the ability of that acid to split up into ions. And all of those 7 strong acids turn 100% into their ionic form. Arrhenius' definition of a base was something that would have the concentration of hydroxide ions increase when you dissolve it into water. Well, let's use the Bronsted-Lowry definition, a bit more modern, and we'll say that Bronsted-Lowry bases are those substances which can accept protons. Strong bases are the soluble metal salts of a hydroxide ion. So basically it means anything in the alkali metal column, hydroxide, or in the second column, calcium, strontium, or barium mixed with hydroxide is an example of a strong base. Now what happens is that, as you can see, as I look at my before picture on the left, here is H2O, and this is a hydrogen ion that's going to be donated over here to the NH3, ammonia. Make sure you keep those straight. When that occurs, all that's left behind is a hydroxide ion, and you form the ammonium. So in an acid-base reaction, the acid in this case happens to be water, and water can act as what we call a weak acid. When you react acids and bases with each other, you learn that they can make a salt and water. And in fact, they can also make carbon dioxide gas if it's something carbonate that is being reacted. Another thing you have to get comfortable with is this textbook writes acetic acid CH3COOH. And it's kind of a nice way to write it because it shows out here at the end of this carboxyl group is a hydrogen ion waiting to be given away. And what will happen is that it will donate this hydrogen ion. It will neutralize the hydroxide ion. The hydrogen ion gloms onto the OH, and you have liquid water forming. This is a misleading kind of reaction because it shows the sodium now attached to the acetate ion, but it's not really because that's all dissolved in water, and so that's why it would be an aqueous solution. When a strong acid reacts with a strong base, the net ionic equation is always quite delightful. As you see this process going on here, hydrogens and hydroxides make water. And we did this HCl and NaOH a number of times. The NAs and the Cls can never make precipitates in this context, and therefore they are spectators that are canceled out. And the players are the hydrogen from the HCl and the hydroxide from the NaOH. There are some metathesis or double replacement reactions that cause the formation of a gas. And here is an example of one that we also did last year. You can take chalk, calcium carbonate, react it with hydrochloric acid, and you do get the predicted ionic salt and the predicted water because calcium carbonate is a base, hydrochloric acid is an acid. But just memorize, anytime you're adding an acid to something with carbonate, CO2 gas is also the expected product that you're going to get. And that's what I just said. Here are examples of sodium hydrogen carbonate down on the second equation reacting with hydrobromic acid, a strong acid, and you will get sodium bromide. There's a salt. Here comes the CO2 gas, and here is the liquid water forming. Now notice that here they show liquid and gas, and that's how they would be written if you were writing a net ionic equation. These two guys, sodium and bromide, however, this is a general molecular type equation. In reality, these two ions are not attached to each other because they're highly soluble in water. Now, some of these are getting into more nuances or trivia, so I'm not going to get too excited about it right now. Another kind of gas that can form is if you have a sulfite, like this strontium sulfite, reacting with an acid, hydroiodic. You make your ionic compound, strontium iodide, you make your liquid water, but now you'll have sulfur dioxide gas come bubbling off. And that's actually fairly soluble in water, by the way. Why would this reaction be make you very unpopular? If you look at when you have a sulfide reacting with sulfuric acid, sodium sulfide and sulfuric, you make sodium sulfate and you get stinky rotten egg smelling hydrogen sulfide. So there are a number of reactions that involve gases that also, that involve acids that can produce gases. Now I'm going to stop here and we will pick up oxidation and reduction reactions and a few other types of reactions in the next part of this lecture.